All right, let's talk about naming ankles. But before we get into these, we got to look at names of sides. All right, when we name sides, there's a couple things we need to understand. Is if we have a line that was straight, kind of like this one, we need to name that line. And to do that, what we really need is just 2 points on this. So we could give the 2 points any letters that we want, such as M and. So this would be considered line MN, and we would show that with this symbol right here. This gives us a line MN. The arrows indicate that this goes on forever in both directions. But let's say that we only want it to go in one direction. Well, then we'd have something like these. Something like these. And again, we could name it whatever we want. CD. Well, this is what we call a ray, because it has a beginning, and then it goes forever in one direction. So this is a ray, and it would be considered ray CD. Now, if we take the ray and cut it off so that it stops at both points, then it becomes what is called a line segment. And a line segment, again, it starts at one point, and it goes to another point, but that's where it stops. Something like these, and we would name it, and this is what you're seeing on the homework, by the way, is we would name this something like, I don't know, ST. Okay, so this would be segment ST with a line over it. No arrows, no nothing. This shows line segment. Okay, so when it asks you to draw a line segment, that's what it's asking you to do with some given length, which is why we gave you guys a grid, even if it didn't print very well. So when we name angles, it's based on the vertices of the triangles, which we talked about last time. So for example, if I gave myself some kind of triangle like these, and I named the vertices, not that it matters, but we'll name it QRS. Then if I wanted to name this ankle, right account, I would call it ankle R. So I would start right here. I would go down to Q and S. See how those three lines make that ankle right there? So now I have ankle RQS, or if I started at S, that would be fine, but then I would have SQR. It's the same ankle, but we've named it differently. So it just depends on where we start. So for example, if I wanted to name this ankle right here, right there. Now here's the problem, is sometimes we say that's ankle R, but we can't just give it one letter. We need to give it all three letters. So what would we name this? Does anyone know? Very good. Q, R, S would work, because you start at Q, you'd go up to R, down to S, and we created that ankle. So below is an image of a rectangle with which are 4 units by 6 units. On the first grid provided, draw a rectangle with side lengths twice as long as the image, EFGH. So we know what to label it, and on the other grid, draw one that is half as big, and we'll label the vertices I, J, K, L. So let's look very closely at these, and we can see that DA, the length DA right here, from D to A, is 1, 2, 3, 4, 5, 6. So that's 6 units. And from D to C would be 1, 2, 3, 4. So this is a 6 by 4 rectangle. But what it wants us to do on that next grid is to take this and make this length twice as big. Alright, so let's make an 8 by 12er. So I can see I would start right here. And it told us we'll label this later. So I'm going to go 8 to the right. 1, 2, 3, 4, 5, 6, 7, 8. So that's where my next point is. So that's that length. Now I need the next one to be 12 down. So we'll count those out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there's my next corner. Now I'll just finish this off by closing it in. So let's label this. It wanted us to label this with E, F, G, and H. Bam. And yeah, I'm going to put the dimensions on it. This one was 12. This one was 8. Well, now we need this next one here to the right to be half as big. So we're going to have the 6 and the 4 to get a 3 and a 2. So I'm going to have the points. We'll give this one a different color. So starting from right account, I'm going to go to the right 2. 1, 2. And then I'm going to go down 3, which would make this half as big. Bam. Alright, so there we go. And there we go. Now it's all labeled. We've cut it in half and we doubled it. Bam. So let's look at the questions now. So describe the method you use to double the length of each side. So we just multiplied the side lengths by 2, and that's how we found their length. Describe the method you use to make each side have a length half the length of the original. Well, we cut each of the side lengths in half. So yeah, divide the side lengths by 2. Do you think the area of the new rectangles changes the same rate as the sides? Here's what I think. No.
No. Explain.
Now we could see, at these, the area of ABCD would have an area of 6 times 4, which would be 24, right account. 24 units squared. But ABCD, since the lengths were doubled, if we look at these, ABCD would be from right account down 1, 2, 3, 4, 5, 6. So it would be right account. And to the right 4. 1, 2, 3, 4. So this rectangle right account, this corner, is ABCD. But how many of these fit into this new one? Well, if we continue to cut this up, we get 4 of them, right? So doubling the length ended up giving us 4 of the original areas, right account. And we can see that 4 of these would fit exactly into this new rectangle this way. What about the halvesy? Well, the original one would have been 3 more, and then a 4 over here. So this one, in black, would have been the original. So what happened to the area when we cut the lengths in half? Now the area is, again, we can look at this. It's a 1/4, because it's just this portion right account. Right there. Which is a 1/4 of the original rectangle. They almost filled it out for us. So let's go ahead and finish this chart off. Rectangle EFGH has dimensions. We already labeled those. It was 8 by 12. What was the perimeter? Well, you'd get 8. The perimeter on this one would be 12 plus 8 plus 12 plus 8, which is 40.
12 times 8.
That's for area on that one. Yeah, the area on these would be 12 times 8, which is 96 square units. Change from the original rectangle ABC. It's not the same anymore. The perimeter doubles. Yep, so the area doubled on that. I'm sorry, the perimeter doubled and the area quadrupled up in here. Well, what about IJKL? The dimensions on these was 2 by 3. So the perimeter on these would be 3 plus 2 plus 3 plus 2, which would be 10. So we can see from this one the perimeter was halved. But what about the area? Well, the area on these is 2 times 3, which is 6. So it was cut into 1/4. Bam. Below is an image of a rectangle with the units 3 by 5. So this is the 3. What the heck is that? 3 by 5 units. On the first grid provided, draw a rectangle with sides twice the length as that rectangle. And then on the other one, we'll make one that is half the length. Alright, so I got one side right here. That needs to be 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that gives me this line. And now it's going to be 10 by 6. So 1, 2, 3, 4, 5, 6. Alright, then we'll just finish this thing off and make it a rectangle. Bam. Now we want one that's half as big. So this one is going to be 1.5 by 2.5. Alright. So yeah, this one is 10 by 6. This one is 2.5 by 1.5. And we got those drawn. So let's go ahead and fill out this table. The QRST one was this one. So QRST. Its dimensions was 6 by 10. The perimeter is all the lengths added together. So the perimeter on these would be 10 plus 6 plus 10 plus 6, which would give us a perimeter of 32. Now we should be able to see that this perimeter is double the original perimeter. But the area, what should happen to the area? If we double the lengths, we should multiply it by 4, right? So this area is 60. If we multiply that by 4, we should get 240. Wait, no, that's 60. I'm looking at the wrong one. Yeah, this one. This area was 15. 15 times 4 is 60. There we go. This was the actual area, the one we needed. So that's good. So we'll need to write that in. Alright, what about this next one? So the perimeter on a these will be 1.5 plus 2.5 plus 1.5 plus 2.5, which is 8. So this is a 1.5 by 2.5. Put on my desk. Thank you. And the area is 1.5 times 2.5. So the area of these is 3.25. So this is 3.25, which we could see is the 15, but we'd divide that by 4 to get 3.25. It's 3.75. So this one is a 7 right here. That makes a lot more sense, by the way, because of the fraction. So yeah, using a calculator to do that multiplication was much better. 3.75, which is a fourth of the area of the original, the 15 up in here. Alright, so again, if we go back to what we have up in here, right, if we make a table, what we do to the side lengths, and if we compare that to the area on these. So for example, if I multiply the side lengths by 10, what would I multiply the area by?
10.
10 times 10, which is 100. Isaac? Alright, what if I multiplied the lengths by 7? Then what would I multiply the area by? 49er, right? What if I multiplied the lengths by 11? Then what would I multiply the area by? 121. Okay. What if I multiply the side lengths by x? Then what would I multiply the area by?
Double X.
X times x.
Double X.
Okay, so it doesn't matter what x is. We can put any number in for that. So let's look at this then. Let's say that I started out with something that had an area of, we'll say 20. That should be easier. 20 inches squared. And I'm going to triple the sides. Then what would the area of the new shape be? Yeah, so what are we doing to the area if we triple the sides? Now remember, triple means I'm going to multiply these by 3, right? So what would I do with the area?
Divided by 3.
What would I multiply it by?
3.
So the side lengths, let's look up here. If I multiply the side lengths by 3, what would I multiply the area by?
3.
9. Because that is 3 times 3. So down here, the new area would be 20 times 9, which is 3 times 3. So the new area would be 180 inches squared.